So as you saw, given an LTI system and its impulse response, you can completely characterize the output of the LTI system or any arbitrary input using a particular integral. And this integral is what we will call as the convolution integral. So this integration between the input and the shifted versions of the impulse response is what we denote as the convolution, and it is denoted by this symbol. So as we saw before, the convolution operation, all it does is just take the signal, represent that as sum of impulses, and for each impulse or each shifted version of the impulse, we know what is the output. So we just take the shifted versions of the output, which is the impulse response, scale it with the corresponding input signals value, and then add them together. So how do we graphically represent this? So let's see how to graphically represent this. So let's take an example of some arbitrary signal h of t. So let's say this is the impulse response. Okay, this is an output signal, so we can represent that using this graphical notation. Now let's say we want to understand the output of the system, which has an impulse response given by such a signal, for some other input. Let's say the input is something that looks like this. What do we need to do? So we can represent this x of t as this impulse plus this impulse plus a bunch of impulses, right? Now what is the corresponding output? So corresponding output for this impulse is the impulse response as such, h of t. And what is the corresponding output here? It's the shifted version, shifted. And then of course you have to multiply with x of tau 1, and then once again this is another shifted version, and then the final output y of t is the sum of all these things. So we can represent this compactly using this integration notation. Alright, so what does this integration tell you is that this shifting and adding is equivalent to this integration representation, which says that graphically what this means is, take this signal h of t minus tau, which is the impulse response, do the time reversal. Remember here the variable of integration is tau. So t is a constant inside this integral, and tau is what that varies from minus infinity to infinity. So in this case, when you say minus tau, the minus of tau represents time reversal. So you have to time reverse the signal to compute h of minus tau. So you first time reverse the signal, and then for each value of t that you want to compute, that is, you want to compute the output y of t, right? So I want to know the output at, let's say, 1 second. Then what is the output at 1 second? The output at 1 second is x of tau h of 1 minus tau d tau. Now if I want to find the output at, let's say, half a second, then it is this integral. If I want to find the output at, let's say, 2.5 seconds, then it is this integral. So for a given value of t, you plug in that t here, which is as good as shifting the impulse response by that amount, okay, and then multiplying with your input signal and then summing them up together. That's exactly what we did earlier, right? So in this case, what does it represent? It simply says that you are adding the scaled shifted versions of the impulse response. That is your convolution operation. And graphically, how does it get represented? It gets represented as 3 different steps. First step, take the time reversal. Okay, so let's see this with an example. Let's say if your impulse response looked something like this. Okay, so this is -1, this is +1. Time reversal. First step is to reverse your signal in time. Now shift it for a particular value of t. Now let's say I'm going to shift it for t is equal to, let's say, from -1. So if I shift it for t is equal to -1, then my signal moves to the left in this case. Then multiply with your x of t and then find the area. Multiply, find the area, and that is equal to the signal's value at y of -1. Now shift it, let's say, to t is equal to -12, and it moves towards the right. Once again multiply with your signal, compute the area, that will be y of -12. Now you have to do this for all possible values of t. In other words, you have to do all values of t equals -infinity to +infinity, which is as good as moving your impulse response from the left to the right, like a shifted version, multiplying at each and every point with x of t and then computing the area. Maybe this will become a little clear when we see a video of the convolution. So this video shows the convolution of the rectangular signal of the triangular signal. As you can see, the triangular signal is the impulse response which is flipped, which is basically time reversed, and then shifted from -infinity to +infinity. At each and every point of the shift, you multiply that with your signal, compute the area under this product, and that would be your output. That's exactly what is happening in this convolution. To be more concrete, so this is your input, this is your impulse response. The flipped version of the impulse response in this case looks exactly the same because of the impulse response being an even signal. But if it is not, you can clearly see that there is a time reversal. But nevertheless, so let's find out what is the output at time t is equal to 0. At time t is equal to 0, your impulse response is present in this location. Basically, here we have tau. The x-axis here is tau. Okay. Now, at t is equal to 0, which is the shift of your impulse response, you get the signal to be present at this location. Multiply that with your input. When you multiply that with your input, then the product is basically this curve. Find the area under the curve. So, what is the area of this curve? Right? Area of this curve is this rectangle plus this triangle. What is the area of this rectangle? It is just nothing but 0.5. And what is the area of this triangle? It is nothing but 0.5 times 0.5. The total area is 0.75. That's exactly what we get. And let's say we have to keep moving this right to the left and right, and then compute the output at each and every point. Now let's say we want to find the output at t is equal to 1 second, which is basically y of 1, which means you have to shift the impulse response by t is equal to 1 second, the time reversed impulse response. So the impulse response now moves to this point. So remember, the center of the impulse response was at 0. Now at t is equal to 1, it moves to the point at t is equal to 1. So if we're trying to compute at t is equal to -1, then the impulse response would be centered around this point. Alright. At t is equal to +1, now you have the impulse response to be centered here, basically the shifted impulse response. Now you multiply that with your input, the product is this signal. And what is the area? The area is basically the area of this triangle, which is nothing but half times half times half, right? So just exactly 0.125, that's what we get. So you can do this for each and every value of the time instant. If you want to compute the signal output at t is equal to, let's say, 2 seconds. Now then you move this impulse response, shift it to be centered at 2. Multiply with your input. Obviously, there is no overlap. So in that case, it will be 0. So if you want to find out the output at, let's say, t is equal to half, then shift your impulse response to be centered at, of course, we are shifting the time reversed impulse response to be centered at half. Now multiply, then whatever you get here, the area, in this case it is half, so y of half will be equal to 0.5. So this is exactly how convolution works. You reverse your impulse response, keep shifting it from left to right at each and every point, multiply that with your input signal, take the area of the product, and that single number will be the output value at that time instance. Okay. Let's see another video where the impulse response is not symmetric, not even. So this video shows the convolution of the rectangular function with an impulse response where the impulse response is not even, and it is one of the asymmetric functions that we have seen before. You can clearly see that it is getting reversed, time reversed, and then it is shifted from the left to right and multiplying together at each and every point, and then computing the area gives the output of the input signal. So what we have here is the impulse response h of t is equal to 1 for t less than or equal to half and 0 otherwise, which is the same as the input also. Now what we need to do is find the output, which is the convolution of h of t and x of t, which is basically the integral we just saw, which is x of tau times h of t minus tau d tau. Okay, so what is x of tau? X of tau is 1. X of tau is 1 when tau belongs to the interval minus half to plus half. And what is h of t minus tau? So h of t minus tau is 1 when t minus tau is less than or equal to half. Absolute value of t minus tau is less than or equal to half. In other words, this means that tau has to be in the interval t minus half to t plus half. So we have the signals x of tau and h of t minus tau both to be 1 only when tau belongs to both these intervals simultaneously. Otherwise it will be 0. So what we need to find out here is the intersection of these two intervals. If you find the intersection of these two intervals, then we know that in that intersection, the product of these two signals together is 1. In all other values of tau or in all other regions of tau, it is equal to 0. So what is the intersection of this region? So the intersection of this region, let's see how it looks like. So we know that minus half plus half is the first region. The next region, let's say t is now negative. Okay. So if t is negative, then of course minus t minus half is on the left hand side. So it starts somewhere here and ends somewhere here. So this is minus t, or rather t is negative, t minus half, t plus half. Of course, if t is really small, let's say t is minus 10, then this interval will be somewhere like minus 10.5 to minus 9.5, which also has no intersection. So which means t has not only should be negative for this to happen, but also it should not exceed, or it should not go below minus 1, because if it goes below minus 1, then we'll have an interval which is starting from this side and then ending here, right? So this interval has 0 intersection with minus half to plus half. So that should also not happen. So whenever t is in the range of minus 1 to 0, we have an intersection of this interval. Similarly, whenever t is in the intersection 0 to 1, basically t is now positive, then you start at a point which is after minus half and end after plus half. Of course, once again, if t is a big number, let's say 10, then once again you will be starting at 9.5 to 10.5. So 9.5 to 10.5 has no intersection with minus 0.5 to plus 0.5. So you need to have once again t to be a small number which is between 0 and 1. Then the intersection will be this region. Okay. So now we have two different regions for the output to be non-zero. In other words, we'll say that the output is the integral between minus half to t plus half, which is basically this interval starting from here till here, okay, and 1 d tau when t belongs to minus 1 to 0, and it is equal to t minus half to plus half when t belongs to 0 to 1, which is basically this point and this point, okay, and it is 0 else. So evaluate this integral. So if you evaluate this integral, we get t plus half minus half, which is t plus 1 for and when you evaluate this integral, you get half minus t minus half, which is 1 minus t in the interval 0 to 1 and 0 else. How does this look like when you plot? So let's see how it looks like when you plot. So from minus 1 to 1, it is non-zero. In all other areas, it is 0. What happens in minus 1 to 0? It is t plus 1. So at minus 1, it is 0. At 0, it is 1. So you get a line like this. And what happens in this region? You get a line like this. So basically what we are seeing here is convolution of a rectangular function with itself has now given us a triangular function. So this is a very interesting property which we'll find very useful later, that the convolution of the rectangular function with itself gives us the triangular function. Now it looks so complicated when you do it analytically, right? But if you observe this graphically, it becomes much simpler to see what the convolved output is. Let's see graphically what happens. So let's say this is h of tau and this is x of tau. Now let us say that we want to first find out y of 0. So if you want to find out y of 0, what do? You multiply x of tau with h of 0 minus tau, okay, which is nothing but h of minus tau. What is h of minus tau in this case? Because h of tau is even or symmetric, h of minus tau also turns out to be the same thing. So you multiply these two signals, which is nothing but the same signal again, because it exists from minus half to plus half and the amplitude is 1. Now y of 0 is nothing but the area under this product. The area under this product is the area under this curve. The area under this curve is 1. So y of 0 is 1. Now let's say I want to find out y of minus 1. How would you find out y of minus 1? So you plot h of 1 minus tau. What is h of 1 minus tau? H of 1 minus tau is h of minus tau shifted by 1. Where does that go? It appears here, where we have half 3 by 2. What is the product here? It is 0. So what is the overlap here? The overlap is 0 because the product of x of tau and h of 1 minus tau is 0. They do not have any overlap. So the product is 0. Similarly, what we have at y of minus 1 is also 0. So how to find out the values of the rest of the points? All you have to do is shift. So let's say we want to find out h of 0.5 minus tau. How do you find this? Shift the signal by only 0.5 or half times. How does that look like? It looks like this. Now what is the product? Now the product looks like a small rectangular function which is from 0 to 0.5. What is this area? The area is 0.5. So we have 0.5 here, which is y of 0.5. Similarly, if you want to find out h of minus 0.5 minus tau shifted by minus 0.5 times. In other words, this is the signal you get. Once again, we have the area to be 0.5. So we get the triangular signal very easily when we graphically convolve. So what turned out to be a long process analytically turned out to be a very simple process when you graphically convolve. Okay. So let's see another example. So in this case, the impulse response of the system is given to be e power minus t u of t, and the input is now given to be x of t equals u of t, and we need to find the output. So let's do the same as we did before. Convolution minus infinity to infinity x of tau h of t minus tau deta. So let's first substitute the input. The input is simply the unit step function, meaning it is 1 for t greater than 0, 0 otherwise. So in other words, when you substitute that here, we get x of tau to be equal to 1 when the limit is between 0 to infinity, and when all other values from minus infinity to 0, x of tau is 0. This is 1 times h of t minus tau deta. Now let's substitute for h of t minus tau, which is nothing but 0 to infinity e power minus t minus tau u of t minus tau d tau. Okay. In other words, this is, remember the integration is only with respect to tau, which means t is a constant here, and e power minus t comes out, and we are going to integrate only e power tau. And what about the unit step function here? The unit step function here says that it is 1 when t minus tau is greater than 0 and 0 otherwise. So what does this mean? So this means whenever tau is less than t, this unit step function is 1, otherwise it is 0. Okay, but we already have tau going from 0 to infinity, and now we are saying that it is 1 only when tau is less than t. So which means now tau runs from 0 to t. Okay, that's it. D, which is equal to. So what happens if t is negative here? If t is negative, then this entire integral is 0 for t negative. Okay. Only for t positive we have this expression. Let's integrate this. We have for tau as such t0, which is negative e power minus t, e power t minus 1, which is 1 minus e power minus t. Okay. So the output now is y of t, which is equal to 1 minus e power minus t when t is greater than 0, 0 otherwise. In other words, the output is y of t equals 1 minus e power minus t times u of t. So this is the output of the system that we are looking for. So it so happens in this case, the analytical way of computing the output is easier than the graphical way. So you have to keep in mind how to compute the output, that there are two ways, either analytically or there is a graphical method. In some cases the graphical method turns out to be easier, in the other case the analytical method turns out to be easier. So depending upon which is easier, you can use one of these techniques to find out the output of the LTI system.